Let's take a look at various application architectures that have been in play over the years, and we're going to kind of look at this from a historical perspective because I think it's helpful to see kind of how things change over time and how we kind of revisit previous architectural decisions going back to the mainframe era and right up through to today with single-page applications in browsers and on mobile devices. Just as a kind of a way of determining the kinds of things we want to think about when we're looking at architecture, these are some questions that we want to keep in mind as we look through some of the history of this. So first of all, what is traveling over the wire? We know that we're going to have multiple computers, servers, database servers, application servers, mobile devices, other kinds of interfaces that we're going to use to interact with the application. But when we're thinking about kind of what's moving across the wire between, say, the client that we're using to access the application and the servers that are actually providing the functionality, what are we going to send? Some examples of that, for example, are HTML. So for sort of first generation web applications, HTML was the thing that was moving across the wire. You'd make a request to a particular website by putting a URL into a browser, and then all of the rendering of that website would take place on the server, and it would return to you as HTML that the browser was going to render. And you kind of go back and forth like that. In more recent applications, we're actually going to use a representation of just the data that the application is going to manipulate, and that's often going to be transmitted in the form of JavaScript object notation, or JSON. Secondly, we could ask, where is the view created? And we're talking about a view here. We mean basically just the information that's presented to the end user. In that first generation web application, the view was created on the server side. The URL went to the server from the browser, and as I just mentioned, the server would be responsible for creating the HTML that gets sent back and displayed to the user. In contrast, in more modern web applications, or say on a mobile device, the client is where the view is created. So it's taking place inside your browser. It's just data that's coming across from the server, and the client browser application is what's responsible for actually creating the display. The third question is, where is the business logic? And by business logic, we basically just mean the encoding of the practices and policies and procedures of the organization that's sponsoring this application. So if you're a retail establishment, there's going to be a bunch of business rules around how you sell things, how much you charge for them, how you allow people to pay, how you allow them to log in, how you allow them to create shopping baskets, and those sorts of things. If you're a bank, you have a lot of rules about withdrawals and deposits and so forth. So by business rules or business logic, we just mean the way that the business or the organization conducts itself. And in many cases, the application, in order to be able to conform to those requirements for the business itself, is going to encode that business logic in the software that actually implements the application. So in the early kinds of applications, say on a mainframe, where the only functionality that was really viable was running on the mainframe itself or on the server side, all that business logic would be encoded in the program on the server. But in more recent days, some of that business logic is also implemented on the client side. So for example, if you think about a sign-up page to create an account on a website, the business logic underlying that creation project might say that when a new user signs up for an account, they need to be able to provide us a password, and they need to confirm that they've typed that password in properly. So you'll see those two fields on the display that allow you to type in a password and confirm it. Now, the reason for the presence of both of those fields ultimately is this business policy of the organization that says, hey, let's make sure that we don't have users putting in passwords that they forget or that they mistype. And the implementation of that policy on the code in the browser is to have those two fields. So in that case, the client and the server are kind of collaborating together to enforce that business rule, that business logic. Fourth, we want to think about how persistence is managed. So when I talk about persistence or data persistence, what I mean is the way in which the application stores data that needs to stay around over a longer period of time. So we're not thinking about the things like session cookies or those types of things. We're thinking about account data, purchase data, product information, catalog data, and those sorts of things. In the early going, some of that information would have just been stored in a sort of an ad hoc way on the server. You'd create some kind of a flat data file that was of your own design, and you'd use that information to store business data on the server. More recently, actually this is not really that recent, but with the advent of standalone relational database systems, that has become the domain of a database management system, like a relational database, say Postgres is what we'll use in this course. And there's a dedicated piece of software that's provided to the business logic as a service that allows it to store that information. Fifth, where is the controller? This is the question of where does the control of the application take place. So how do we orchestrate the interaction between the user interface and the server and the implementing of the business logic and making sure that the user sees the right information at the right time and navigates to the right locations within the application and so forth. And then sixth, just some other things that we need to be thinking about when we're talking about an architecture. Things like input validation. So the example that I gave previously about typing in a password and then confirming that password would be an example of input validation. But we might also do things like if we ask a user for an email address when they're signing up for an account, we might do some validation in the browser to make sure that what they typed into that field looks like a valid email address. We also need to think about how do we actually render those views, the information that is going to be displayed to the user for them to consume when they're using the application. That could be done in a whole variety of different ways. We could use a templating system. We could use dedicated HTML components. We could use a screen from the old-fashioned mainframe applications and so forth. We need to think about how we're going to access data. Is that going to be done using server-side only code? Is it going to be done to extract information from the client side, sending a request to the server for that information in other ways? And then finally, how do we deal with security? That usually falls into two things. The first is the question of authentication, which is finding out who you are and verifying that you are who you say you are. That's usually something that involves an account name and a password, for example. And then authorization, which has to do with what you're allowed to do within the application. So once we've authenticated that you are a certain user, what are we going to allow you to do in terms of authorization? So let's take a look at some specifics of these various architectures for application development. We're going to start all the way back in the mainframe era and then go through the client-server era, kind of the early part of the web, and then what we would think of as more modern single-page web and mobile applications. So a mainframe was a very large computer system that kind of was a self-contained computer that could handle a considerable amount of data processing functionality. This is an illustration of one built by a company called Univac. And this picture probably dates into the 50s. And the person standing in front of the computer is a very famous computer scientist. Her name is Grace Murray Hopper. She's actually, was when she retired, an admiral in the U.S. Navy. And she was responsible for the invention of a very important computer language called COBOL. You can see the manual that she's holding there conspicuously in the foreground. COBOL stood for Common Business-Oriented Language, and was kind of one of the first high-level programming languages that was used for more business applications. The other game in town at the time was a language called Fortran, which was an acronym for Formula Translator, and it was used as a primary language for doing scientific applications. So Grace Murray Hopper is a very significant computer scientist. She actually is still, she's passed away now, but she is still celebrated at something called the annual Grace Murray Hopper Celebration of Women in Computing, which we've sent numerous students to over the years to participate in. Actually, we have a connection to Grace Murray Hopper. This is a photograph that's taken in Nussbaum 123, that large classroom in the Nussbaum building. And the guy with the crazy big tie is Leon Adkisson, who was the person who founded our systems program in our department. He actually retired at the time that Taylor hired me back in 2008. And he was a friend of Admiral Hopper, and she's there in this picture wearing her naval uniform. And the story that Leon told me about this photograph is that he had been introducing Admiral Hopper And she just got tired of all of the adulation that he was heaping upon her, and she literally grabbed the little lectern thing away from him and forced him to be done so she could actually give her presentation. The mainframe that we saw back here in this photograph, usually it always was stored in some sort of a climate-controlled laboratory that was attended by people in white lab coats and stuff. Admiral Hopper's attire here was probably not typical for the people who operated a mainframe, but it was very closely controlled, very difficult to access, and was only made visible to the outside world by just wires. And the kind of connection that you would use when you were accessing applications that ran on mainframes in the early going looked like this. So this is an example of a teletype, and it's what sort of stands in as the user interface for a mainframe application. You can see that, first of all, it prints on paper. There's no screen, there's no mouse, there's no icons, there's no graphics. You just get ordinary printed output, just like an old-fashioned typewriter. You type on this really clunky mechanical keyboard that makes a ton of noise, and your mass storage devices are actually here on the side. You can see this roll of yellow paper is actually a mass storage medium. What you did was you would take that roll of paper and you'd string it through this section of the teletype, and this was actually the print head. What you would do then is you would type a command to the mainframe on the keyboard that would, for example, list the contents of your program. And everything that got printed here on the paper would also be encoded on this paper tape as it spooled through the print head. And the tape would come out here and sort of spill down on the floor. And the idea was that each of the characters that was printed on the terminal would actually also be encoded as a series of holes in the tape itself. So you'd see every few fractions of an inch, there'd be a variety of holes, and those holes would basically be bits that would encode the characters that were coming out of the terminal. Once you finished doing that listing, you could then take that roll of paper tape and put it in your backpack and come back the next day, and you would then load it into this portion of the machine, which is a paper tape reader. And you can see here in the top portion of this kind of clear plastic cover, you would open that up and you'd put the paper tape there on some little sprocket that would pull the paper tape through that read head, and it had little fingers, mechanical fingers, that would sense whether there was a hole or not a hole, and use that to encode the bits in each of the characters that was on the tape. And it would basically type in the contents of the tape onto the paper and also send the characters to the mainframe in the back room so that you could reload a program that you were working on previously. So quite primitive by today's standards, but this is what stood in for a user interface in days of old. You also had ways of using this information remotely. So this is first of all, here on the right side, that's a telephone, in case you don't recognize it. They don't look like that anymore, an old style dial phone. And here was the handset for the phone, which, you talk in one side and you listen in the other side. But what it was used for in the mainframe era was to communicate remotely to a mainframe. So you might be across town or across the country, and you'd make a dial-up connection to the mainframe. And this device here, it's called an acoustic coupler. You'd take the phone handset and place it in these sort of foam cups here that would sort of grab onto the phone. And on the earpiece of the phone, the acoustic coupler would listen to what was coming from the other side. And on the mouthpiece side of the coupler, it would make noises that would be sent over the phone line to the mainframe. Now these guys operated at what was called 110 baud, and a baud is just sort of a fancier, older style word for bit per second, basically. You could think of it that way. So these things ran at 110 bits per second. Now just to contrast that with today's technology, the Ethernet backbone in the science building at Taylor actually runs at 100 megabits per second, which is 100 million bits per second. So our backbone network in the building is literally 1 million times faster than this kind of technology that was in use in the 50s, 60s, and 70s. There's a little bit of an advance going on in the user interface here in the form of a video teletype, or what was called a glass TTY. So you can see this is a little bit more modern looking piece of equipment. You still have a keyboard, although it's a nicer one than that mechanical keyboard on the teletype, and you still have a display that's really not doing a whole lot more than what the paper did on the teletype. You're still talking, you'd still use this kind of a device over a modem. It was pretty slow, it didn't have any graphics, or there's no mouse in this picture, there's no icons or pointers or anything like that. So you're basically interacting with the mainframe on the other end of a connection in a similar way, but you didn't generate all that crazy paper and stuff. So this is a significant improvement over the old-fashioned teletype writers. So there's some history for you. It's a better time to be in computing now than it was back in the 70s. So if we think about kind of what does this architecture look like, and we'll kind of evolve this diagram across these different architectures. This is an example where in the middle here we've got sort of the server, right? And in the case of a mainframe, all we have is that mainframe computer itself. And all of the code that's executed in this setting is running on the mainframe. Those teletypes obviously they were completely mechanical, so there was no processor or anything like that in the teletype, not even in those glass teletypes. They were really just an electronic device that didn't have anything even remotely resembling a CPU. So all of the smarts is the mainframe in this case. And I've added this little annotation here that says that the application code basically runs entirely on the mainframe. Behind the scenes, in terms of where do we store our business data or our organization data, the mainframe, in the early going, there wasn't really a standardized format for databases like we have in relational databases, for example, now. There are actually a whole variety of competing services that would provide data persistence. But really, you were just talking to the file system. It's like you were just opening a file, reading and writing a file in whatever format you cooked up. There wasn't a standardized kind of service for data persistence. And all of this stuff, sort of from here down in the picture, was running in a server room someplace, again attended by people in white lab coats. And the way that you communicated, on the user interface side, sort of above this line, we had that dumb terminal. Or we could, if we had additional funds or we were a little later to the game, we might have a glass TTY. But we would be basically getting output onto paper or a screen without any graphics or anything like that, and we'd be typing in at a keyboard. But what's going back and forth over the wire here, and this is literally just a wire, just a three-wire cable connection, a send, receive, and a ground. When you push the key at the keyboard, that would be sent across that wire as a series of bits that represented that key. And when the mainframe wanted to send something back to you, it would send text characters encoded in something like ASCII that would then be printed on the page or displayed on the CRT display in the glass teletype. So very primitive interactions. But if we step back a little bit and kind of ask some other questions about how this impacts the operation of applications and how it works within an organization, one of the benefits of this, it kind of doesn't seem like there should be many benefits because it's so primitive, but one of the benefits is that all that application code is running in one place. So if I have to upgrade my application, I've got to go to those guys in the lab coats that are running the mainframe and say, here's the new version of this code, and they can install it on the mainframe. And from that point forward, everybody who's at a dumb terminal somewhere out in the organization, which might be in the same building, the same state, or a different country even, depending on the communications capabilities, everybody would immediately be updated to using the new version of the application. So although the user experience is kind of primitive, it's actually quite easy to manage in some sense, in that you only have to upgrade your application or the underlying operating system or the device drivers or whatever in one place, because there's just one mainframe, it's in one location, and you can make changes to it in a quite straightforward way in that one spot. Kind of the next major generation of application architectures was facilitated by the advent of the personal computer. Prior to this, you had to access your mainframe application using one of those types of devices that I showed you in the previous section. But now you had at your desktop a personal computer that had a bona fide CPU in it, had its own memory, had its own storage, had probably a slightly better display, although graphics and the typical Windows and mouse interface still hadn't really shown up yet at the beginning of this era. But you had two places now where you had some intelligence. You had some intelligence on the desktop in your PC, and you also had some real computing power still in the back room that provided services and storage for you. Now we're sort of moving away from using the mainframe as that main storage thing into a slightly different approach to this that we'll refer to as client-server. So there's two elements to this. On the server side, what we're meaning now is instead of this giant monolithic mainframe machine, the server is going to look something quite a lot closer to what we would typically see in a server room in recent years. So this is just a simple photograph of a server room that has a whole bunch of different servers of various types and network connections and Ethernet cables and so forth. But each of these rack-mounted devices, right, one of these slots in the rack is a server box, a physical computer that can provide services elsewhere in the organization. On the desktop then, we had something like this. This is a very early IBM PC, which would have been introduced in about 1984, I think. This particular model had no hard drive. You can see here there's two floppy disk drives, which used the 5 1/4 inch floppies, which were floppies that actually still flopped if you shook them in your fingers. And you notice that although there is a video display, it's not really showing much in terms of graphical sophistication, and there is no mouse in this picture, right? So that was not a thing yet. But the principal difference is that this is, although it's sort of primitive and low-powered by today's standards, this is a bona fide computer. So the processing tasks can be shared between these guys in the back room, which are principally now going to be storing files and offering up data, and these machines on the user's desktops. So the architecture picture now looks quite a lot more sophisticated. We still have kind of this division here across the middle of the page where this is the server side, and on this side we have the client, which is the PC. So hence the name of the architecture. On the server side now, instead of having all of the application code for the entire application running on the server side, we've got sort of a little bit more focused approach to what's going on the server. So first of all, data persistence, instead of just having file system here, I'm actually calling this DB for database. So this could have been an actual relational database, sort of an early primitive version of those pieces of software, but a much more sophisticated, higher level approach to storing application data. And then this RDBMS shows Relational Database Management System. That's the acronym. So there's a piece of software that's running on those servers that is providing services for data storage and access, and that's backed up on disk by these database files. Furthermore, within the database itself, it would be possible to write code, which, because they're running inside the database itself, are referred to as stored procedures. If you want to know more about that, take the database class. But this is application code, as I've indicated here by this little annotation. So you've got application code running on the server side, but all it's doing really, or the focus of it at this point, is principally managing data for the application. On the other side, on the client side now, we have so client runtime. This would be the application code that's running on the client, right? So this is the big new change here between mainframe and client server. We've now got application code running here on the server, but we've also got it running here on the client. That means that those desktop PCs, despite their relative primitive capabilities, we're actually helping make for a better user experience, giving more feedback, giving more verification, allowing the user to do more work on their desktop because they now had a computer right there. And we could use the native user interface on those PCs. The one I showed you didn't really have much in the way of graphics, but certainly as the IBM line and Apple and other manufacturers of that time, as they advanced the capabilities of their machines, we started to see bona fide graphical user interfaces, which obviously made the application much easier for mere mortal users. Now at this point, the connectivity between these two, I'm showing here local area network. right? So not only did we see the advent of personal computers on people's desktops, but we also now started to see real networking. So Ethernet networking would have been available at this point in the history of application architecture, and connected over a local area network. The traffic that's moving, what are we communicating over the wire, again, to that question? Because the principal function of the server was to just provide access to data, normally what was coming into the server would be something like a SQL query. So the application itself would want to display some information for the user, and the app would then send a SQL query to the database management system. It would go off and access the database, maybe run some stored procedures, and then respond with information that the client could display back to the user in the form of just kind of tabular data, right? If you think about a relational database, all that the relational database model stores is two-dimensional tables. And that's the kind of information that would get sent back to the client, which would interpret that kind of raw query result in a way that could be displayed in a friendlier manner to the user, allow the user to add things, change things, modify things, and then as more bona fide graphics came into the picture, display charts and graphs and so forth based on those data. So quite a bit more sophisticated user experience, but let's go back and think about that question of how do we maintain these kinds of applications. In the mainframe era, it was really easy because we had exactly one mainframe, and if we wanted to update application code, we could do that in one spot. In this environment, it gets quite a lot more complex. Not only can we have, as I showed in this photograph here, many servers, each of which is going to have to be running application code. They would have to all be updated. The good news is that they're all in the server room, right? So your system administration staff has a fairly straightforward job of upgrading all of these servers. What's more difficult is these guys, because these could be distributed all around your floor, your building, your city, even across the country or around the world, and you had to figure out how am I going to get updates to all of those client workstations when I want to upgrade my application, because usually the changes to an application take place on both the client and the server. It's particularly challenging because the storage medium that we have here is floppy disks. So what would usually happen is that you would make many copies of floppy disks that didn't have much capacity. So you might say a non-trivial application might require 10, 20, 30 floppy disks to go to each user all around the planet. If you had thousands of users, you'd have to make thousands of duplicates of all those disks and get them sent out. And then you'd have to rely on the end user to install those updates on their PC, which they might not want to do, they might not be qualified to do, they might do wrong. So what we did was we sort of created a richer environment for application development, but we created kind of a system administrative nightmare, trying to figure out how do we upgrade all of these applications in the field. Now we get to the advent of the web. So now we're into the early 90s. We've still got a bunch of personal computers out on desktops. We've still got server rooms full of rack-mounted server machines. But now we have the web browser. And the focus now in delivering functionality starts to switch over to delivering these apps in a web context. And I'm going to distinguish two generations of web applications. So this is what's now called Web 1.0, or kind of the early versions of the web. And here's what the application environment sort of looks like now. Again, we have this kind of distinction here between client and server. Some things are similar in terms of the basic architecture. First of all, for data persistence, we still have a typically relational database management system, and it's using some database files to store business and organizational data persistently. Some new things that are going on here, though, on the opposite end of the server architecture, we have this new piece of software called a web server. It's important, if this is still kind of unclear to you, to distinguish between two different uses of the word server. When we talk about a piece of hardware, like one of those rack-mounted machines in the server room, we're talking about a physical piece of hardware. That would be a server machine. I'll try to distinguish those. But when we're talking about servers, we can also think about servers that are pieces of software. So while all of the stuff in this portion of the architecture might be running on a server machine, server machine, there's different, the other boxes on here are different processes. They're different programs that are running on one or more of those server machines. So the web server is a process that's responsible for listening for requests from web browsers and sending responses back. The RDBMS is itself a server process that's responsible for handling requests for data access and serving back the information to the other program that requested them. So when we're interacting with the web server, we've got our browser here on the client side, and what we're going to do is send requests. So you're familiar probably from previous courses with the idea of an HTTP GET request or an HTTP POST request. GET is the type of request that's sent when we just want to fetch a fresh web page. So when we put an address into the URL address bar on the top of the browser, that sends a GET request. Or when we click on a button, that often sends a GET request. A POST is usually what's used to send additional data to the server, usually in the form of a filled out web form. We'll obviously go into that in quite a lot more detail as we look at the specifics of the implementation of these things. But the question of where do we, or what information goes across the wire is answered by this diagram. We're going to send requests, HTTP requests from the browser to the server, and what we're going to get back in this early version of web apps is going to be typically HTML. The server is obviously also going to send other kinds of data like images or movies or things like that, but the principal thing that we're asking is to get an HTML page that the browser then can render inside the browser software. So the web server is the piece of software that's listening for these requests and then satisfying them with responses. And you notice that the thing in between here now, instead of being a local area network or just a wire, I've said internet, right? So the internet largely in the way that we currently understand it as a global network for sending information across different networks within it. Now, the third piece here on the server side that sits between the web server and the data persistence layer over here is where the application logic lives. So you can see here there's only one place where I've annotated app code, and I've put this in another box here called CGI. So CGI, yeah, it's not a graphics reference in this sense. It actually stands for Common Gateway Interface. And this is basically kind of early versions of web applications. The web server would get a request, and it would look at that request and say, it would make a decision between one of two things. Either it was a request, say, for a flat file, like an image, and if it received that kind of request, it would say, oh, I know how to do that. I'll just go back into the file system, fish out the image, and send it back to the browser on the other side. But if it was asked to do something more sophisticated, the web server itself didn't really know how to do anything other than serve files, so it would then punt to the CGI program. So this would be another standalone program, often written in C in the early going, that would be able to create dynamic content. So when the user logs in as a particular account, the CGI program would be able to ask the database, hey, do you know about this user? And the database could go out and look in its data and say, yeah, here's the details of that user. Maybe something like, here's that user's shopping cart. The CGI program could then formulate that shopping cart as an HTML page and send it back to the web server to have it deliver that HTML back to the browser so the user could see their cart. The CGI program could do anything that a modern web server application environment can do, but it was really quite clunky. It was quite slow. There wasn't a whole lot of optimization going on there, but that was where we got all the smarts for the application. Now it's interesting that we went from all of the smarts on the mainframe and none on the dumb terminal. Then in the second generation with client server, we now moved some of the application functionality forward to the client. So we had app code running on both the client and on the server. But now the pendulum has kind of swung back. We can see that there's no app code bubble here on the client side anywhere. It's only got intelligence on the server side, which in a way seems like kind of a step backwards, right? The reason for that was that in the early going, browsers were not particularly sophisticated. They couldn't run general purpose application code like they do now. So we're left with only one choice as a place to put application logic, and that is on the server side. Now that is sort of clunky, right? It made for arguably less friendly applications from the user experience perspective than what you had in the client-server era, but it did have the positive side effect of making it much easier to manage updates and changes to these applications, because every PC in the field had a standard browser. I could assume as an application developer that everybody that's going to be using this thing is going to have access to that browser, and I've just got to make sure that my application code on the server side conforms to the expectations of the browsers that I've got installed across my organization. And when I want to do an update, I've just got to update it in that one place again. So from a management and system administration perspective, in a way, I'm kind of going back to the mainframe era, but in sort of a positive way, right? Because I'm still delivering a better application experience to the user, because the browsers at this point, were bona fide graphical user interfaces. They could do graphics, they could do mice, they could, let you interact with them in a richer way than what you had from the teletype. But I still could manage all my application code from one spot. Let's move to the second generation of the web, what's commonly called these days Web 2.0. And here's an illustration of what that architecture looks like now. Again, we have this boundary between the servers on the bottom and the client on the top. We've still got a browser going on here and on the client side. And then we still, on the server side, have our database management system and its backing files for persistence. We've still got a web server. I guess I've included an explicit mention of the file system here, that the web server can still serve things that it knows how to deal with. And in a similar sense, when the web server gets a request that it doesn't know how to deal with, it can still pass that off onto another piece of software. Instead of calling this just the CGI layer, I've kind of upgraded the naming here to call this an application server. So this does a similar job to what the old-fashioned CGI programs used to do, but they're much more sophisticated environments for developing applications. And we're going to use this type of an approach in this course. So the application server that we're going to use is a JavaScript-based thing called HAPI, H-A-P-I. And it does everything that the old CGI things could do and a boatload of other stuff. And of course, because that's where a lot of the smarts for the application live, we've got application code that's running here on the server side. Notice, however, that now we've also got some code running on the client side. So again, the pendulum is kind of swinging back, right? We went from mainframe, all on the server side, to client server with a partitioning of the application logic, to Web 1.0 back on the server, to Web 2.0. Now we're back on both sides of the client-server boundary. I've listed this here as GUI code. It's primarily there to be able to take information from the user and send it to the server, or to retrieve information from the server and format it nicely for the user. So instead of just having a dumb browser, which was sort of the modern equivalent of a dumb terminal back in the day, we've now got a smart browser that can run application-specific code and present things in a way that's going to give a much better user experience. And that's enabled by this little box I've added to the browser that says JavaScript, right? JavaScript is a bona fide programming language that runs in the browser and can essentially execute whatever code we want to be able to use for displaying information to the user. That's what really enables this process. The other thing here that I've mentioned is AJAX. This is an acronym that you may have seen used in the past. What it stands for, or stood for originally, is Asynchronous JavaScript and XML. So what we've got going on here is when we still have traffic from the browser to the server going in the form of HTTP posts and GET requests, but the idea of AJAX here is that those requests can be made asynchronously. The distinction again between synchronous and asynchronous is that a synchronous request or a synchronous function call in a program has to run to completion before the next thing can happen in the program. Whereas an asynchronous function can kind of go off in its own thread of control, complete it on its own, and then return back to the main thread of control, which continues to run. So we can think of the browser as having its own thread of control. So inside the browser runtime, there's going to be kind of a series of operations: look at the keyboard, deal with a key press, get stuff from the user, show the contents of a graphic, that kind of stuff. There'll be that one thread of control that kind of keeps the user interface going. Okay. Now, if we were to send requests to the server in the way that's shown here synchronously, what would happen is that thread of control that's keeping the user interface alive, keeping it responding to user input, would have to temporarily pause, wait for the network request to be made, which is going to mean sending a request to the server asking the app server to do some things, the app server asking the database to fetch data, formulate a response, and send it back over the wire in some form that the browser can then interpret. Now, depending on the speed of the connection and the performance of the server-side machines and software, that could take quite a long while. I mean, it might a long while. It's kind of a relative term, right? But it might be seconds before a response comes back to the browser. And during that time, the user interface is effectively paused because we're making that request synchronously. That doesn't yield a really super great user experience because you're constantly sort of sitting there waiting for something to happen. Instead, what we do is we do this request asynchronously. That's the first A in AJAX. So we send a request to the web server, and then we sort of go back to running this main loop. The browser continues to respond to user input, still allows you to scroll and read stuff and type things into forms and whatnot. But there's another thread of control that started up on the browser. I'll just draw a smaller little arrow circle. And that represents the process or the thread that's waiting for the response to come back from the web server. When that process completes, the same web server, app server, database management server, and back out, when that process completes and then the response gets received by the browser, this thread gets woken up and handed the information that was received from the server side. And it can then go ahead and update the display, show a new graph, whatever it is that particular application thread is supposed to do, at the same time that the main thread of control continues to operate. Okay, so that's finally we're getting a really good user interface, a really good user experience going on. The user doesn't have to sit and wait for stuff to come across the network, but that information is still being given back to the user as soon as it's available in the browser. So the first A in AJAX stands for asynchronous. And we're going to spend quite a lot of time in this class talking about how do we do asynchronous programming to make that kind of thing possible. The J then was JavaScript, and that, of course, is going to be implemented on the browser side in JavaScript, which is why that's the next part of the acronym. And then so asynchronous JavaScript and XML. So the X stands for XML. This is a data interchange format that could be used to send sort of arbitrary data back and forth between a client and a server. You'll notice here in the network connection portion of this diagram that I'm showing that we can still deliver HTML, right? The application server might give back a full HTML page that the browser will then render. But it can also send back this other format called XML. XML actually derives, both XML and HTML derive from a common data formatting mechanism called SGML, Standard Generalized Markup Language. So if you look at an XML file, it looks remarkably similar to an HTML file. There's going to be angle brackets and tags and attributes and data and that kind of stuff. But whereas HTML is constrained to only express things related to browsers, XML can be defined to store any kind of data at all. And you can actually create standardized representations for specific kinds of data in XML. And at the time that this AJAX idea gained prominence, XML was kind of the de facto standard for interchange of data between client and server. So that's why the early versions of this Web 2.0 architecture used XML. Now it turns out that XML, although it works totally fine, wasn't really super friendly to JavaScript. And what was emerging in the early going was another format called JSON, which stands for JavaScript Object Notation. And this is just a data exchange format that looks a lot like a JavaScript object, and it can contain nested objects and nested arrays and arrays of objects and so forth. So it basically gave us the same kind of capability that XML did, in that we could interchange arbitrary information between client and server, but it was done in such a way that was sort of much closer to what the JavaScript code running in the browser expected. And it's really simple to translate JavaScript object notation as a data exchange format into real live in-memory objects and arrays in JavaScript. So although we still loosely refer to this kind of architecture as an AJAX architecture, in fact, most applications these days use JSON instead of XML, but we haven't started calling it AJAJ. It's still sort of called AJAX. Okay, so that's the Web 2.0 architecture, sort of what most new web applications are being written in, or written to use. If we think again about the kind of the system administration of a system that uses this architecture, it might seem like we were opening ourselves up to a whole lot more hassle than we were in the Web 1.0 architecture, because now we've got code that runs on both the client and the server. However, remember that now we've got a really capable network, the internet itself, that's connecting together the clients and the servers. And in fact, when you first access a Web 2.0 application like Gmail or Google Docs or something like that, the early portion of that connection is actually transferring across the wire the latest and greatest server or client-side code, the JavaScript that's going to actually make that work on the fly. So we don't have a separate update step where when we release a new version of our software, we've got to send that all out to all of our users. It just sort of goes along for the ride when the user connects to our application. So not only do we, at this point, have the benefit of a richer user experience because we've got a browser that has programmability in terms of our application-specific JavaScript, we've also, because of the networking technology, pretty much eliminated the need to worry about upgrading our client software on our end users' machines. For this next architecture, what I'd like you to focus on is kind of this box here that represents the browser runtime. You can see here that I've added the JavaScript box here, but it's kind of a minor portion of that browser runtime software. In the early going, even in the Web 2.0 era, the use of AJAX in this asynchronous communications pattern was relatively minor in comparison to a typical application. So you might have portions of a web page that would be updated dynamically in that fashion, but you'd still be relying on an HTML page that was largely generated on the server side. So we had richer user experience because we could update things dynamically and asynchronously, but we weren't really relying super heavily on that capability to display the whole user interface. So the next step, and this is sort of where we are these days, we'll just refer to as a single page application. Sometimes that's abbreviated to SPA for SPA. And the difference here, as you'll see in that corresponding box, is that I've given a lot more emphasis to the JavaScript and a lot less for just kind of the underlying browser runtime. And that's intended to convey the notion that a very large portion of the user experience, the user interface, the user interaction with this app is going to be carried out by JavaScript code that's running in the browser. I'm not intending to suggest that the browser is less capable or can't display the same kinds of images and media and text and so forth. That's all still the same as it was in the previous generation. But the emphasis on having a lot of application code in JavaScript running on the browser is really what distinguishes sort of the early Web 2.0 from this single page application architecture. So as in the previous slide I said that this was mostly GUI code, right? It's going to update portions of the display as you go. Now I'm saying this is bona fide application code. So a significant portion of the development process is tied up in making sure that we've got working software on the client side as well as the things that are going on the server. The components here on the server side are exactly the same as they were in the previous slide. Another difference besides a much heavier reliance on JavaScript on the client is the information that's being communicated. So we're still going over the internet, which is great, and I've replaced the information that's being sent to the browser with just JSON. Notice that I'm not even saying HTML here anymore, because for the most part, in a single-page application, the server side is dedicated almost exclusively to serving data to the client, to the browser. And the browser itself, by merit of this application code, is responsible for rendering that data in the form of HTML and other representations of that information completely on the browser. None of that information is really being transmitted over from the server in terms of an HTML page or something like that. The browser is doing that all dynamically by merit of running this more sophisticated application code. On the other side of the connection, I've said here now, instead of just saying get and post, which are sort of the two most common HTTP operations, I've said HTTP verb. And we're going to see when we start talking about RESTful APIs that there's a lot more sophistication available to us in HTTP than what you might be aware of right now. And that's illustrated here in this little table. You'll recall the notion of kind of the CRUD operations. It's not a very pretty acronym, but it stands for create, read, update, delete, which are basically the four operations that you want to be able to do on data. I want to make some new data, that's the create. I want to read existing data or retrieve it. I want to be able to update it, and I might want to be able to delete it. So those four operations are really at the core of any kind of data processing system. And it turns out that HTTP is friendly to that kind of a pattern. So we're familiar already probably with the GET and the POST requests that we can make in HTTP. And those correspond in a RESTful API, which we'll go into much more detail on. A POST request corresponds to creating something new. And just intuitively, if you think of a POST request as something that you normally will send when you have a user fill out a web form, what you're asking the user to do is give you some new information, a new account, a new credit card, a new service request, whatever it is. And on the server side, that's going to turn into creating new data that's going to be stored persistently in the database. On the other hand, if you're querying from a web server with a GET request, now you're going to be retrieving information from the server. And so you're going to get, here's a list of your of the contents of your shopping cart, or here's a list of accounts that you're managing, or whatever that is. So the GET request corresponds to that retrieve operation in the CRUD pattern. And then there's other HTTP verbs that are maybe less well known or have been less well known that do the other two CRUD operations. So there's two associated with updating existing data, right? Give me a new phone number for your account. That would be the patch request. And then if I want to remove something on the server side, I can send a delete request, right? I no longer want to have an account with you. Please delete me. So the pattern here of using these different HTTP verbs in order to specify those kinds of data manipulation operations is really the bread and butter of the way that your application code on the client interacts with the server. You're going to send those verbs with additional information to say, you know, what do I want to create or what do I want to delete? And what you're going to do is get back JSON that basically gives you the results of that request, whether it's a list of the accounts that you requested in the GET request or a confirmation that you've successfully updated your phone number in the case of a patch request. So we're going to unpack this in a lot more detail as we go here, but this is pretty much, this picture gives you a pretty good picture of what we're going to develop in terms of an application by the time the semester is over, a full stack web application. Interestingly, importantly, because we've now kind of isolated the display of information and the interaction with the user from the serving of information and data persistence across the client and the server side of this connection, we can use this in other contexts. So the final portion here is the idea of a mobile application. And what I've illustrated here by kind of graying this lower portion out is this is exactly the same as what we had in the single page application picture. And in fact, we're still sending HTTP verbs and getting JSON results back out. But what I've shown here is that instead of this being a browser, it could also be a native mobile app. So you could be running something on your mobile platform of choice with all of the nice GUI controls and good user experience for a mobile device. And you can code this to use exactly the same interface that the single-page application has. So now you have a lot more flexibility in terms of how you provide access to this application to your end users. If they want to come over a browser, you can write code that works in the browser and uses the same server-side components as if they were going to come in over a custom mobile application. The great news is you can reuse all this stuff on the back end. You only have to build that one time, and then you can have mobile users, browser users, and so forth by merit of the fact that this interface doesn't change. This is a great example, if you think of it from a software engineering perspective, it's a great example of encapsulation and reuse and all those other kinds of good things that we like to see in a well-architected application. And it's kind of been enshrined now as the best practice for developing both rich web applications, the single-page application kind of thing, as well as the pattern of choice for accessing data in a mobile application.